We're going to start our traditional discussion of circuits by talking about current. And current is just the flow of charge. Now, when I think of the flow of something, like the flow of a river, it's got to go somewhere. Now, when I'm measuring this current, what I do is I set up a lawn chair right there. And I get a counter like one of those greeters at Walmart. And I draw a red line across that wire. And every time a coulomb of charge goes across that line, I click. Another coulomb of charge goes across that line, I click. Another coulomb, I click. The number of clicks per second per unit of time is the flow. If I use the definition here, if you replace delta T with 1 second, the current is just how much charge in coulombs goes across that red line. Okay? Now, here's the thing. We measure current in amps, and that unit was defined first. Because an amp is a perfectly reasonable amount of current. If you've got some kitchen device that's got a motor in it, like a blender, it's going to have about half an amp going through it. Unless that device has a heating coil in it, it's always going to have some fraction of an amp going through it. And so an amp is a reasonable amount of flow. But because of that definition, we're stuck with our definition of the coulomb for charge, which is a huge amount of charge. And that's just because that's how much charge goes past that red line in 1 second in a typical household device. Now, here's the thing. Ben Franklin, Uncle Ben, did us a huge disservice when he called the charge on the negative, on the rubber rod negative. Okay? You remember that Ben Franklin thought that this charge was an invisible substance that you were either putting extra on or you were taking off. Now the invisible substance, it turns out, was electrons. And when Ben thought he was putting extra of this on, like he thought he was putting extra of this stuff on the glass rod to make it positive, that's why he called it positive, it had extras. What he was really doing was taking electrons off. And so we got it exactly backwards. Now if we look at any wire, it's neutral. It's got just as many positive charges as negative charges. Even if I have a huge current going through this wire, it's still neutral. It's not charged, it's neutral. It's just that the electrons are moving through the lattice work, through the metal. Now, we typically play a game. Instead of thinking of the electrons going one way, we make believe that positive charges are going the other way to get rid of a whole bunch of minus signs. In other words, that would represent a wire. And I have just as many positive protons as negative electrons. Now, if an electron were to move to the left, that makes that positive charge look all by its lonely. Okay? And if the electrons keep moving to the left to fill in the gap, that looks like the positive charge is moving the other way. Now, there's only one experiment that I know of that can tell me whether it's electrons moving to your right or whether it's positive charge moving to your left. We call that the Hall experiment. It's hard to do. We're never going to do it. So for our class, it really doesn't matter whether we think of it as electrons going one way or positive charges going the opposite way. Now it turns out, trust me on this, we're going to be much better off if we do what the rest of the world does and talk about conventional current. Conventional current is we pretend that this wire is a plastic tube and that positive charges are going through that tube, the opposite direction that the electrons are actually going. Physicists do this, electrical engineers do this, the electrician that comes to fix your socket at your house does this. Everyone does this to get rid of those minus signs to make up for Ben Franklin's mistake.